In the next tutorial, we'll be looking at adapting the service API to accommodate multi-objective optimization. Now, with multi-objective optimization, of course, you can just simply add the parameters together or come up with some simple scalarization function. Here, we'll be covering a state-of-the-art method, which involves optimizing the expected hypervolume improvement. It's okay if you don't know what that is. We'll be going over that in the notebook. So in this multi-objective optimization example, like I said, we'll be using the service API. Multi-objective optimization is sometimes abbreviated or acronymed to MOO. And we specify this a few ways. We've got the, an objective properties class that we'll use. And we'll start off with, we'll also talk about setting thresholds for our objectives in order to focus the optimization to certain regions on the Pareto front, or that front of optimal trade-offs. So we've got the Axe client from the service API. We've got objective properties, which will help us define multiple objectives. Some of the typical plotting helper functions, as well as a multi-objective function, which is this sort of combination of the Brandon function and another analytic function, the current function, as far as I understand. So we instantiate our two objective problem, and we create our Axe client and set up our name, whatever we want, our parameters, and our objectives here. So for the objectives, this will be a dictionary mapping from the name of the objective to an instantiated objective properties class, where we assign these two variables. One is optional. So first is whether or not the objective needs to be minimized. And then the second is a threshold that we can specify, or we can leave it off, in which case the algorithm itself will infer appropriate objective thresholds. So this can be, this is a case where scientific domain knowledge can really come in handy, because as an optimization practitioner in the physical sciences, with that domain knowledge, you're often aware of reasonable limits on certain parameters. In other words, it's kind of like asking the question, if the performance for this particular objective, for objective A, was lower than this amount, it would effectively be useless in a practical setting. So if you know that kind of information, like hardness below 20 gigapascals, a vigorous hardness value below 20 gigapascals isn't of interest to the algorithm, then you could set it to something like 18 gigapascals for the lower this threshold to help gear the algorithm towards a higher one. And we'll also go over some more results towards the end about how setting those thresholds affects the optimization algorithm. We've got our evaluation function, which will be taking in, this time, the Brandon kern function. It just needs to take a torch.tensor. If you have your own multi-objective function that gets evaluated, you'll probably just be passing in the normal parameters, not as a torch tensor, but as floats, individual arguments, things like that. Then here we're returning a dictionary, and it's important now in this case that it's a dictionary because we're returning two outcomes, and we need to be able to clarify which outcome value corresponds to which objective. So we've got the A objective, and we're passing in a tuple of our, this will essentially just be a float, and the standard error, which is set to 0 here. In just about any real chemistry or material science task, that error will almost certainly not be 0. And so you can leave that blank, or you can use your own domain knowledge or something that comes from a simulation or something you know about the experimental equipment to set that value explicitly. And then we have our second parameter, and we're also passing a tuple there. Then we run our optimization like normal for the service API, where we get the next trial and then evaluate our objective based on the specific parameters that were suggested, and then complete the trial, reporting that back to the AX client. And this is where our visualization starts to look a little bit different for the multi-objective problem. So we can pull out our objectives from the AX client's experiment, then the optimization config, the objective, and these objectives that come from that. And then we can compute the posterior Pareto frontier. So here we've got posterior referring to the model in light of the previous data that we've had so far. So this is calculated, and this is the frontier of the optimal trade-offs between our objectives, or at least what the model thinks are the optimal trade-offs based on the data that it's seen so far. So we pass in our experiment, some data using axclient.experiment.fetch data, and then our primary and secondary objective. Key here being that we can visualize two objectives easily, while AX doesn't directly support three-dimensional visualization of objectives, as far as I'm aware. That is also a possibility. You could use a library like Plotly or Matplotlib to do that yourself. And then we have absolute metrics, which is a list of outcome metrics that should not be relativized with respect to the status quo. Now, the status quo is something that you can define in the experiment to act, as the name implies, a status quo for your experiments, a baseline, something to compare against. So if you don't want those to be relativized, then you pass in this is absolute metrics. And then we have the number of points, or in other words, the number of points that will get simulated for the. Finally, we render that, and we can use a particular confidence level, which affects the bounds of our error bars, essentially. It's not that confidence level interval. So next, we'll be covering a little bit more about the actual algorithms available here, and compare those to a quasi-random search. So, like it says here, multi-objective optimization covers the case where we care about multiple outcomes in the experiment, but we don't necessarily know beforehand a specific weighting of those objectives, or a specific constraint on one objective that will produce the best result. And this is often the case because in the physical sciences, because essentially no material science problem is ever truly single objective. For example, there will always be a material cost associated with something. And so while you might have performance metrics, or maybe one particular performance metric that's really important, or often reported on in the field, there's usually a cost metric associated with it as well. And often there are multiple performance metrics. So you might want a large bulk modulus and for a material to be very hard, or you might want some other combination of mechanical or chemical, other physical properties. So let's talk a little bit about Pareto optimality. And this case where there's no single best solution. So the goal is to identify a set of optimal trade-offs such that any improvement in one objective means deteriorating another. Here we have kind of an example set, and we'll say the goal is to minimize both of the objectives F1 and F2. And the question being here, what is the Pareto front here? If we, and these points in red are the Pareto frontier, because going back to this statement up here, an improvement in one objective means deteriorating another. So take this this blue point here, for example. There are points that are better in both objectives, whereas y of 1 is the best in f1, and there's nothing that is better than that in f1. And then likewise here, if you were to degrade f1, have that, or sorry, if you were to try to find the point that improves, has a better value of f1, that to do so would mean you'd have to decrease the performance of the other objective. So specifically for y of 2, if you were to find something that is even better in f1, which is this y of 1 red point, f2 has to get worse in order to find that next point. So let's also talk about the quality of the Pareto front. And this we'll start using the notion of a hypervolume. So in 2 dimensions, the hypervolume is an area. In 3 dimensions, the hypervolume is just a normal volume as we consider it in 3D Cartesian space. And then in higher dimensions, we have the higher dimensional analogs of volume, or the hypervolume. And the idea here is that instead of using some scalarized function, like an addition of our objectives, or some other kind of simple analytical function of the objectives to scalarize it into a single objective, what we can do is suggest candidates that have a high probability of improving the area in a 2D case, the volume in a 3D case, and the hypervolume in these higher dimensional cases associated with our Pareto front. And in terms of setting a reference point, a threshold that was mentioned before, it's suggested that that should be set to be slightly worse than the worst value of each objective that a decision maker would tolerate. And it shows that the gray area is the hypervolume in the 2 objective problem. So let's look at setting these objective thresholds and how that affects the actual optimization here. So in this first plot here, there are no, let's see. Yeah, so the first plot shows the points without the objective thresholds visible. And so in this case, they're set to be very low, far below the origin of the graph. And then the second shows this much narrower region that it's focusing to. And then the third one shows an even narrower region. And so you can see that in the middle graph, we have many more points that are actually falling along the Pareto front, 2 or 3 times as many points due to that focusing of it into a region. Now for the next one, while the points aren't, the Pareto points aren't exclusively focused in that region, it has helped the algorithm to push it a little bit further into the region of interest. Yeah. They're still more focused there than in the second example. Okay. And they go more into the math of the algorithm for these 2 acquisition functions in the notebooks mentioned here. I believe both of these are, or sorry, a notebook here, and then the 2 papers here. This next part goes over using the developer API to make some comparisons between different acquisition functions and compare that to the quasi-random search performance. And I'm not going to go over a ton of the specifics of the developer API, but I'll point out a few places where that show how it's using the lower level building blocks that can give you some more control, but requires more lines of code than the service API. So moving here, let's start with the range parameter. So instead of using strings or dictionaries with strings to define the different parameters, we'll specifically use a range parameter, and there's also another class choice parameter, and we'll pass the parameter type as one of these parameter type objects, constants as well. We'll create our search space from a list of the parameters. We'll create metrics based on custom classes that we define, pull those metrics together in objectives, pass the list of objectives to multi-objective, create objective thresholds in a similar manner, and then create our multi-objective optimization configuration by passing in our objective and objective thresholds. Then we can also define some utilities for building our experiment, a function here that returns an instantiated experiment object using our search space and our optimization config, as well as a synthetic runner that determines how the experiment is run. In this case, just kind of a dummy runner to since we're using this simple analytic function and nothing too fancy with how the experiment runs and with scheduling. And we'll initialize our experiment using the Sobel model, and that'll be our quasi-random comparison. We'll build the experiment, initialize it with the Sobel experiment, and then run through our batches, generating our candidate and trial, running it, and extracting the outcomes for that. Then finally computing the hypervolume, which we'll use to do some of the comparisons later. So moving down to this noisy expected hypervolume improvement acquisition function, which is the AXA's current recommended algorithm for multi-objective, and then there's an alternative if this one runs too slowly. So we can build our EHEI experiment, run it through in a similar way, computing the observed hypervolume at the different iterations, and then do the same for, first plotting the Pareto frontier based on the model posterior, like we did before, and then using the Pareto algorithm as a comparison here, and following a very similar format for computing the hypervolumes at each of the iterations. Plotting the Pareto frontier for that one as well. And then plotting the observed hypervolume as a function of iteration for each of the three methods that we just did: the Sobel, the expected hypervolume improvement, and the Pareto. So here you can see that the Sobel isn't necessarily generating a ton of candidates along the true Pareto front, which we get a better sense of with the other two functions, especially with the expected hypervolume improvement, where we have a dense sampling of values along this Pareto front, more samples along the Pareto front. And looking at the statistics of the hypervolume, we can see that the expected hypervolume improvement one, which the name sort of implies that it should do the best on getting the best hypervolume. That one's doing the best, followed by the Pareto acquisition function, followed by the baseline of Sobel sampling. So that was the notebook for multi-objective optimization using the AX framework. Uh, and at the top, we can see some of the results that were summarized for when we leave the objectives of effectively unconstrained and when we set thresholds to help guide uh, the exploration of the Pareto front to certain regions. And in the figure below, this is from a paper studying the multi-objective optimization of shape memory alloys. They used finite element simulations, did some experimental validation on the models that they used. These were fairly computationally complex models run in the Abacus software, where the two objectives are a transformation temperature, in this case, the austenitic finish temperature, um, which controls at what temperature these shape memory alloys will recover their original form. The idea being that try to optimize and get that as close as possible to 30 degrees Celsius, and then a hysteresis, or in other words, that kind of lag between the change in temperature and the material, you know, having the corresponding change in property for it. So just to give a little bit more background on shape memory alloys, if you're not familiar with them, these can be used in medical implant devices and actuators and other things due to their unique property that they retain a certain shape at different temperatures. So if you leave it at the cool temperature, it can stay in one shape, and when you have it at a higher temperature, it will change to a different mechanical shape that you can form. And that's due to the transitions of the microstructure in between austenitic and martensitic phases. And so here, what they did is they tried to minimize that kind of lag time or hysteresis, as well as get as close as possible to the 30 degrees Celsius mark. And you can see the Pareto front shown here in the blue dotted line with an ideal solution there, where they used the expected hypervolume improvement acquisition function to guide their optimization results.